2.4 is on one-sided limits. So let's look at the concept and then look at the definition. So first we'll talk about the notation for left-sided limit. So just write left down. And so if I say the limit of a function f of x as x approaches a, and then put a little negative up there, that means from the left equals L. So that means x approaches a, and then the negative means on the left. So a picture of that would look something like this. So you have a function doing kind of whatever. Okay, so you're approaching, so here's my a, and then you have a function, doing that. And so on the left is this side, right? So you're looking at a function, your x values are approaching like that. So let me write it like this. So that's my a there, and I have x approaching a on the left, looks like that. So my a value is up here somewhere, and I'm coming in on this side, like this. So that's what we mean by on the left. So it's just basically one side, like that. Okay, and then let's do the right side. Take a gander what that might look like. Right, so for the right, we have the limit of f of x equals L, and we say x approaches a, and then you put a plus there. So the plus means on the right. So x approaches a, and that's on the right. So for that, let's just do a little diagram here. Same kind of thing, so same picture, really, just on the right side. So you have some function. Here's your a, and then here's your x values on the right. So function may or may not be defined there, but you're coming in on that side, like this. So that's what we mean by on the right. Okay, so let's look at a function we defined earlier that was it was undefined, or a limit of a function that was undefined before. So this is the one we look at often to talk about these. So let's consider the function f of x equal to absolute value of x over x. Okay, then find a, the limit of f of x as x approaches 0, and we'll say on the left, and then b, let's look at the limit of f of x as x approaches 0 on the right, and then we've already done this one, c, the limit of f of x as x approaches 0, period. So on this one, and many of these, you want to know what the function looks like. You want to graph the function. So we already graphed this function in a previous video lecture. I think it was 2.2 when we first talked about just limits. So this function basically is undefined at 0. And then to the left, it's -1. And then it's undefined here, and then to the right is +1. Okay, so this is positive 1, this is negative 1. And so when we're approaching, so 0, of course, is the origin, which is right here. When you're approaching the origin on the left, like this, what's the function approaching? So if you're going like this, we can see that the function is getting closer and closer to 1. In fact, it's actually coming in like this on the bottom side, but that's not really the point. So we can see on the left, I'm sorry, I totally messed that up. If you're coming in on the left like this, then you're getting it to be, it's negative 1. So so right here would be the function value as you approach on the left. So you can just say it's negative 1. Okay, so this is equal to negative 1. And then this side, if you approach on this side, we can see you're getting this value. Okay, so it's all of these function values you're getting close to. So on the right, you're approaching 1, like that. On the left, you're approaching negative 1, like that. So this would be, on the right, it's positive 1. And then if you look at both sides, then as we discussed in the previous section, it's on the right, it's not the same. So it does not exist. So you would say this function does not exist. This is a DNE. Or I'm sorry, the limit doesn't exist. So the limit of f of x as x approaches 0 does not exist. So we have a theorem that kind of connects this together. So this theorem basically says, excuse me, the limit of a function exists at a if both the left and right are the same. So we'll write it out, of course, in symbols. It says the limit of f of x as x approaches a equals L if and only if the limit of f of x as x approaches a on the left equals L and the limit of f of x as x approaches a on the right equals L. So if you do get both left and right limits existing, then it equals the limit exists. Then you get this. So that should be intuitively makes sense. So if you have a function that's doing this and it's jumping or something, okay, those sides are different, right? So the limit doesn't exist if you're coming around some value a like that. Okay, so from the on the left, you're approaching. So on the left like this, you get this value. On the right like this, you're getting this value. So they're different. So that limit wouldn't exist. However, the left and right limits do exist in that case. Okay, so let's look at the definition, and then we'll get into more examples. I do want you to see the definition, how it's slightly different, although we will not spend as much time on it as the previous section. So here's the definition of one-sided limit. I want you to see how the inequalities work, because you don't have absolute values for one of the cases. The definition of one-sided limit. So if I say the limit of f of x as x approaches a on the right equals L means that given any epsilon greater than 0, that's always going to be the same, there exists a delta greater than 0, such that, and so this is where we're going to use the difference. So you have 0 less than x minus a less than delta implies, and then the rest is the same, implies the absolute value of f of x minus L is less than epsilon. So this is as close as we want to get, infinitely close, right? So you just keep going. It could be whatever, however small a number you want. You just have to make, and this is on the right, right? So you're having basically x plus delta. So what this means is you're approaching a, but then this interval is then your a plus the delta, right? So if you just solve for x, right, you just add a like that, then your x values are here. So x is less than a plus delta, so you're over here. Okay, so if you just solve for that x, then you're here. But you can't be, it has to be greater than 0, so it can't be over here. It can't be negative. So it shows it all. It implies it's all over here on this side. Okay, and then similarly, let's just put in the other case, but I won't write it all up. We'll just say, if this is on the left, we'll do it in yellow. Then you're going to say, you say 0 less than a plus x, minus x. So I'm just switching the order here. So it still has to be positive. So you're still positive, but it's a minus x less than delta. So when you solve for x, you get minus delta. All right, so it's on the other side. So that implies the same thing. Okay, actually, I'm not going to write that down. That's too confusing. So this case is, so let me draw on this graph a little more carefully, because I actually have that written out for you. So the first case is this graph, and where your x values are in here. The second case is this graph. Right, so here's your a here, and then you're coming in like this, and so that's basically a minus delta, and your x values are in here. Okay, so that's what that inequality would mean. The rest is the same. But really, I mean, if you can really just focus on the first definition, that's good enough for now. But if you want to stretch a little bit your mind, try to see why this is making sense for you and put in some actual numbers and think about it. All right, so let's move on. Take a look at an example. So this is number 19 on page 72 in Thomas 14th. So first one is find the limits of the absolute value of sine x over sine x as x approaches 0 on the right. Okay, and then B is the same basic question, but on the left. Okay, so oops, like that. All right, so so this thing, basically you can interpret it very similar to the one we did above. So what you do in this one, and you don't just grab your calculator or computer and go graph it. You want you want to see what's going on. So let's analyze this a little bit more. Wait a second, that didn't work out very well. Let's try that again. The line like stuttered or something, so it didn't come out. So let's first just look at sine x. We want to talk about y equal to sine x. What does that do? So y equals sine x is this function, and we're approaching 0. So all we really care about is what is it doing around 0. So around 0, it comes down like this, and then goes through the origin and comes back up, right? So that's what we're interpreting, stuff around 0. So we're going to come in like this, and see what's happening. So let's take a look. So as the first one is on the right. Okay, so you're approaching x is like this, and you're approaching 0 this direction on the right. So you have positive values of sine divided by positive values. So what do we know about the function sine x for values just to the right of 0? Are they positive or negative? So basically, we're saying if x is greater than 0, then absolute value of sine x is really just equal to what? Now this is close to 0, so what's happening? Actually, let me say it like this. So if x is in the interval from 0 to, and let's just say pi fourths. I mean, you don't need to say all this to analyze it. I'm just trying to help analyze what's going on. So what does the graph do between 0 and pi fourths? Well, it just does that. Just goes like this, and then at pi halves it hits 1, and then it goes back down to 0 at pi. So it's doing this and this. So in here, that's all it's doing. So if sine x is between if x is between 0 and pi fourths, then sine of x is just absolute value of sine x is just sine x. I mean, so that's it. So you just have the same thing divided by itself, and you get 1. So this whole thing is just equal to 1. And then similar argument to the left, you make the top positive and the bottom is going to be negative. So if you're coming in like this, then the bottom side is negative. So it's just like the x absolute value of x over x function, really. So that's negative, but the top becomes positive. So you have a negative on the bottom, and a positive on top becomes negative. So that ends up being a -1. Okay, I have to move that a little bit. Oh well. I'm gonna run out of space there. Okay, so that's -1. So same kind of interpretation. All right, so try these. Try we're going backwards a little bit, but try number 18. 18a is limit square root of 2x, x minus 1, over, let's try that again, over absolute value of x minus 1, and then b, really the same question as you approach 1 on a different side. So let's just copy that. All right, so this is x approaches 1 on the right, X approaches 1 on the left. All right, so try that one. So pause it. Okay, so pause and try it. Okay, and then when you come back, basically, you should analyze this. You get root 2, and this is negative root 2. So the same kind of rationale as before. 1 is a positive number, but you're still coming on left or right as you approach 1. So you're analyzing basically this the same as we did for the absolute value function. Okay, moving on. So this next one is takes a little bit of work. I might send you some, might have posted already, or I'll send you some information about it. So this is a case that comes up a lot. Okay, so this one you need to know this limit and apply it. Limit of sine theta over theta as theta approaches 0 is equal to 1. Okay, so this is what's used for numbers 23 to 38. So I'll leave that up to you at this point, but that's what you're going to apply. It takes a bit of work to prove this without other theorems higher than this. So I probably will just show it to you and just show you what it takes. It takes a lot of trig and stuff to actually prove that theorem if you don't have any more powerful calculus type theorems. So some of you may have heard of L'Hopital's rule, but we don't have that. We can't use that now. That's proved in future stuff, not until calculus 2. So we may not, or I'll just actually write it here so you have it in your notes. Do not use L'Hopital's rule. Some of you know what I'm talking about. So you can't use it in this class. Automatic 0, basically. Okay, so we don't have it yet. We don't get L'Hopital's rule until Calc 2. So a lot of times teachers, instructors, whatever, they want to show you these quick methods to do stuff, and that's really not the point of math. It's not about quick and get the answer. It's about thinking through it, analyzing it, and being analytical about it. It's not about speed. So I want you to think through these to analyze them, not just use some tricky little rule. It's a very powerful rule, actually, what you can do. Some of you have seen it. Anyway, so that's just a side note because I know it comes up. Don't have a chance to say it in class like I normally would. Okay, so for those questions, apply that formula, and maybe we'll do a couple in the problem sessions. Next, let's go on to 2.5 on continuity of functions.